I know you know that there are storms that can last for several days. There are also earthquakes that can bring down an entire city. But for those who don't know, there is a disaster that can cause massive damage in just a few minutes. That disaster is a tornado. At first glance, it just looks like a spinning column of air. But when it gets stronger, it can uproot large trees, toss vehicles, and destroy houses. Most tornadoes aren't actually that big. Many of them disappear quickly and only cover a narrow path. But on May 31, 2013, a strange tornado formed near the town of Reno in Oklahoma, America. Wow, just got the car blasted by a tornado.
My gosh, this is a monster. The monster is the El Reno tornado. It's massive, fast, and unpredictable.
Until now, it is still recognized as the widest tornado ever recorded in modern history. According to the U.S. National Weather Service, it reached a width of more than 4 kilometers, and in just about a minute, it grew from a thin tornado. It quickly expanded until it became a massive rotating wall of wind and rain. Because of this, many storm chasers had difficulty determining where the true center of the tornado was. Some thought they were still in a safe area, but the truth was, they were already inside its massive circulation. Another reason why the El Reno tornado was unique was its wind strength. Using mobile Doppler radar, meteorologists recorded winds reaching almost 500 kilometers per hour in some parts of the tornado. This is one of the highest wind speeds ever recorded in a tornado. But, along with the important information that scientists gathered here, it was still a major tragedy. 3 well-known storm chasers died while trying to study the unusual tornado. Their goal was to understand how such powerful tornadoes form so that warning systems could be improved and more lives could be saved in the future. But why did all of this happen in Oklahoma? That's because the state of Oklahoma is part of an area called Tornado Alley. This is the region in Central America where different types of winds often meet. From the south, warm and moist air rises from the Gulf of Mexico. From the north, cold and dry air descends from Canada. Meanwhile, from the west, dry air moves in from the deserts and mountains. When these winds come together, the atmosphere becomes very unstable, like a huge machine gradually storing energy. And now that you know that, let me add that the situation became even more dangerous. Because less than 2 weeks before the El Reno tornado, a very powerful EF5 tornado also hit the city of Moore, Oklahoma. So on that day, the meteorologists were even more alert because they knew that another destructive storm could possibly form again. Now, as the ground heats up because of the sun, the air above it also gets warmer. When the air is warmer, it becomes lighter, so it rises quickly into the atmosphere. When a lot of energy is stored in this warm air, there's a greater chance for very strong thunderstorms to form. Meteorologists call this energy KP, or convective available potential energy. Simply put, it's a measure of how strong the force is that pushes warm air upward. On the day of the El Reno tornado, the Cape in Oklahoma was extremely high. This means there was a huge amount of energy just waiting to be unleashed. At the same time, a cold front was also coming down from the northwest and a dry line was moving in from the west. When these met, the hot and moist air was quickly pushed upward. But that still wasn't enough to form a tornado. The most important ingredient is what's called wind shear. This is the change in the speed and direction of the wind as it rises in the atmosphere. When the strong upward wind hits the rotating air currents at different heights, the entire thunderstorm begins to rotate. This is where what's called a supercell forms. The supercell is the most dangerous type of thunderstorm because it has a very large rotating part called a mesocyclone. This acts as the engine of the storm. As it continues to rotate and draw in warm air from below, it becomes even stronger. And when the rotating wind finally descends from the cloud down to the ground, that's when a tornado forms. And on the afternoon of May 31, 2013, all of these elements came together in one place. And in just a few minutes, one of the largest and most dangerous tornadoes the modern world has ever seen was born. But wait, let me pause for a moment. Before we continue the discussion, I'd like to ask for a like and please subscribe as well. This is a big help for us content creators. Thank you. And now let's get back to it. As the night of May 31, 2013 approached, the situation in Oklahoma was getting even worse. On the radar, it was clear that a massive supercell was forming, but according to meteorologists, this was no ordinary thunderstorm. This was what they call an HP, or high precipitation supercell. In this type of storm, a huge amount of rain and hail rotates along with strong winds. Because of this, the tornado itself is covered by heavy rain. In other words, you could be very close to the tornado without even seeing it. This is one of the reasons why HP supercells are so dangerous. Unlike a typical tornado where the funnel cloud is clearly visible, the tornado in this kind of storm is almost hidden behind the rain and thick clouds. There's another event that made the situation even worse. Above the atmosphere, there's a thin layer of warm air called the cap. Think of it like the lid of a boiling pot. While the lid is closed, heat and pressure build up inside. The same thing happened in Oklahoma. Hot and humid air continues to build up below the cap, but it can't rise right away because it's blocked by the warmer air above. As time goes by, more and more energy builds up. By around 4:30 in the afternoon, the cap finally broke. In just a few minutes, cloud formation suddenly exploded. According to weather observations, the thunderstorm grew very quickly. Its towering clouds reached almost 15 kilometers high in a very short period of time. This means that all the conditions are ready for a very powerful tornado to form. At around 5:35 in the afternoon, the first tornado struck from the same supercell, but that wasn't the most dangerous one yet. A few minutes later, around 6 o'clock, a larger circulation began to form southwest of Reno. At first, it didn't look unusual. It was just a small rotating dust cloud beneath a dark cloud. If you look at it from afar, you would think it's just a normal tornado that you often see in Tornado Alley. But there's something that the eye can't see. While the tornado is still small on the ground, something unusual is happening inside it. According to the study by Dr. Jana Hauser and Dr. Howard Bluestein, who used a fast mobile research radar that day, their data showed something different compared to what meteorologists have long believed. For many years, the common belief was that the rotation of a tornado starts at the upper part of the cloud before it gradually descends down to the ground. But in Reno, it seems the opposite is happening. Based on their radar data, the rotation is already stronger near the ground, while the rotation at the higher part of the cloud is not yet well organized. This suggests that the strongest rotation may have started from below before finally connecting to the rotating part of the storm above. This discovery is important. If this process is true for some tornadoes, it means that there could already be dangerous rotating winds on the ground, even if there is no clear funnel cloud visible in the sky yet. And if we wait for the appearance of a large funnel before issuing a warning, it might already be too late. While scientists continue to study the unusual behavior of this storm, the tornado keeps growing. In just a few minutes, it no longer resembles the usual narrow tornado. It gradually becomes a massive rotating wall of wind. This is called a wedge tornado. A wedge tornado is a tornado that is wider than the visible height of its funnel. But in Reno, the funnel is almost impossible to see. Because of the vastness of the rotating clouds and rain, it just looks like a dark wall slowly moving forward. For people on the eastern side of the storm, it doesn't look like a tornado. It just looks like a very dark cloud approaching. And that's the reason why it's so hard to recognize. As it continued to grow, radar confirmed that its rotating winds reached approximately 4.2 kilometers in width. According to the National Weather Service, this is the widest tornado officially recorded in modern history. It surpassed the previous record set by Hallam, Nebraska. That was in 2004. At that point, it was clear that this was no longer an ordinary tornado. It became an extraordinary event that experts continue to study to this day. To better understand how the strongest tornadoes in the world are really formed, But that's not where the unique characteristics of the El Reno tornado end. Its enormous size is just one part of the story. What's even more terrifying is what happens inside the tornado itself. In an ordinary tornado, there is only one main rotating column of air. But according to radar observations from the National Weather Service and research teams studying the storm, El Reno became a multiple vortex tornado. This means that inside the massive tornado, there are even smaller tornadoes rotating around the main center. It's like a huge spinning wheel with smaller ones spinning inside it. And these smaller ones usually have the strongest winds. It's easier to understand this if you think of a figure skater. When their arms are extended, they don't spin that fast. But when they bring their arms closer to their body, they suddenly spin faster. Almost the same thing happens inside a tornado. As the smaller rotating winds get narrower, they spin even faster. Because of this, there are parts of a tornado that are more dangerous than others. On that day, 2 mobile Doppler radars were continuously following and measuring the El Reno tornado. One of them is the Arvin Polo TV. The other is the Doppler on wheels, also known as DOW. These radars collect data faster than regular weather radars. That's why they could better see what was happening inside the storm. Based on their measurements, there were parts of the tornado where the wind reached almost 500 kilometers per hour. This means that El Reno is not only one of the largest tornadoes ever recorded, it is also one of those with the strongest winds measured by modern equipment. But there's another reason why this tornado became extremely dangerous. It wasn't just the small vortices spinning inside the main tornado. As the entire tornado moved eastward, the small vortices inside it also had their own direction and speed. There were times when they would suddenly surge out of the main tornado at incredible speed before returning inside. Because of this, it's almost impossible to predict their exact movement. It's like having many spinning whirlwinds moving together inside a much larger whirlwind. Even veteran storm chasers had a hard time figuring out where it was safe to pass. You might think you're safe because you're moving with the main tornado. But in just a few seconds, a smaller vortex could suddenly veer off and quickly approach your location. This is one of the reasons why the El Reno tornado became so dangerous for those tracking it. And the strange events don't end there. As the main tornado continued to move, another separate tornado formed on its eastern side. This is called a satellite tornado. This is not part of the small vortices inside the main tornado. It is a completely separate tornado, moving alongside the larger tornado. What's even more unusual is that it rotates in the opposite direction. Most tornadoes in the northern hemisphere rotate counterclockwise. But according to meteorologists, this satellite tornado rotates clockwise. It's an extremely rare occurrence. Usually this kind of tornado is weak and disappears quickly. But in El Reno, the satellite tornado was also strong, and it lasted for about 15 minutes while it was moving through Oklahoma. On one side, there was the massive main tornado. On the other side, there was another rotating satellite tornado. They were moving together while the direction and speed of the wind around them kept changing. For anyone in their path, it was almost impossible to predict where the next danger would come from. And as the 2 tornadoes grew stronger, the storm chasers who had been tracking this unusual storm for hours began to find themselves in the middle of their path. While most people were rushing to get away from the El Reno tornado, there was one group that was deliberately following its path. But they weren't looking for an extreme experience or just trying to get a good video. They had a more important mission. The leader of this group was Tim Samaras, one of the most respected storm researchers in America. Tim wasn't just a storm chaser, he was an engineer, inventor, and scientist who had spent many years studying how tornadoes form. His goal wasn't just to chase storms, but to understand them in order to build safer structures and improve tornado warnings in the future. Over the years, Tim developed a special piece of equipment that he called the turtle probe. It is a heavy and sturdy instrument that is placed directly in the path of a tornado. When a tornado passes over it, It measures air pressure, wind speed, and other data that ordinary weather radar cannot capture. This information is very important because most radars are focused on the upper part of the storm, but the turtle probe directly measures what is actually happening on the ground, where the tornado's effects are strongest. Even before El Reno, Tim had already successfully used his equipment several times in different powerful tornadoes. Because of this, he became known as one of the most careful and skilled storm researchers in America. He was not known for recklessly approaching storms. Every move he made was carefully thought through. He would look at the radar, wind direction, storm movement, and various weather models before deciding where his team would position themselves. On May 31, 2013, he led the research group TwistX, or Tactical Instrumented Sampling, in Tornado's experiment. With him in the vehicle were his 24-year-old son, Paul Samaras, and the veteran meteorologist, Carl Yang. Actually, El Reno was not their original target that day. Their initial plan was to study the unusual types of lightning that form in tall thunderstorms. But as the afternoon went by, they noticed that the supercell near El Reno was rapidly intensifying. Based on the radar and atmospheric conditions, they saw that there was a high possibility of a very strong tornado forming. Because of this, they decided to change their plan. Their goal was to place one of their probes in the path of the tornado to collect data that had never been recorded before. They hoped that information would help engineers build stronger houses and also help meteorologists give warnings to the public more quickly. As they approached the tornado, there was another storm chaser ahead of them. Dan Robinson was also driving on the same road while tracking the movement of the storm. To everyone, it looked like they were still at a safe distance, but they didn't know that the tornado was rapidly changing shape. As it grew larger, it wasn't just the center of the tornado that was expanding. Even the rotating winds on its outermost part were quickly moving farther from the center. It became even harder to see its true size because it was being covered, making its size even harder to see. To the human eye, it just looked like rain all around. But according to the radar, that part of the rain was actually part of the massive rotating winds of the tornado. That means, while they thought they were just on the edge of the storm, they were actually already entering its most dangerous part. Storm chasers have long used what is called the inflow notch as a sign of a safe route around the tornado. This is the part where warm air enters the storm. In most tornadoes, this is clearly visible, and it greatly helps in estimating a safe distance. But in El Reno, everything suddenly changed. As the tornado continued to widen, the inflow notch began to close. It was gradually covered by swirling rain and wind. Because of this, it became almost impossible to tell where the tornado ended and where the safe area began. According to reports about the incident, Tim Samaras also noticed this. In their radio communication, he said that there was no rain where they were, even though they should have been in the middle of a severe storm. For a veteran storm researcher, this was a clear sign that something unusual was happening. They were not in the safe part of the storm. They were actually in the path of a rapidly expanding tornado. After this, the unexpected happened. Instead of continuing in the direction most storm chasers anticipated, the tornado suddenly changed its movement. At the same time, its rotating winds expanded further on the southern side. Dan Robinson, who was ahead of TwistX, immediately noticed the danger and managed to get away. But according to the reconstruction by the National Weather Service and the vehicle's GPS records, they were only about 20 to 30 seconds apart. On a normal trip, such a gap would mean almost nothing. But on that day, it was the difference between life and death. As the TwistX vehicle was traveling on Reuter Road near Radio Road, a very strong sub-vortex suddenly separated from the main tornado and passed right through their location. According to radar analysis after the incident, the wind in that part of the tornado was estimated to have reached over 320 kilometers per hour. That force was enough to lift their Chevrolet Cobalt and throw it hundreds of meters away. When the rescue teams found the vehicle, it was almost unrecognizable. That was where the mission of Tim Samaras, Paul Samaras, and Carl Jung ended. But their years of research and the data they left behind are still being used by meteorologists today to better understand the behavior of the world's most dangerous tornadoes and to help save more lives in the future. The tragedy that happened in El Reno served as a major warning to the entire storm chaser community. For the first time in history, well-known storm researchers died while directly studying a tornado. Many people wondered if Tim Samaras, known for being careful and an excellent planner, couldn't survive either. This means that no one should ever underestimate this kind of storm. And it wasn't just the Twistex group that almost became victims. According to reports after the incident, another strong sub-vortex hit the vehicle of the Weather Channel crew, led by Mike Beats. Their SUV was lifted by the wind and thrown hundreds of meters before finally coming to a stop in a field. Miraculously, the whole group survived, even though they sustained various injuries. There was another storm chaser named Richard Henderson. He stopped for a moment to take a picture of the tornado and even sent it to his friend. Just a few moments later, the tornado caught up with him, and he didn't survive. In total, 8 people died in the El Reno tornado. All of them were inside their vehicles when the tragedy happened. After the disaster, another question became the center of discussion among meteorologists. How strong was the El Reno tornado really? In America, the enhanced Fujita scale, better known as the EF scale, is commonly used. The scale has 6 levels for measuring a tornado's strength. It starts at EF0, which causes the weakest damage, up to EF5. The highest level can cause almost complete destruction of sturdy buildings. But there's one important thing that many people don't know. The EF scale does not directly measure wind speed. Its main basis is the damage left by the tornado. For example, if a tornado destroys sturdy houses, uproots trees, and even removes the foundations of buildings, it can receive a higher rating. If only a few structures are hit, the official rating will also be lower no matter how strong the wind is. This is where the El Reno tornado was unique. Although mobile Doppler radars recorded winds reaching approximately 476 to over 500 kilometers per hour, most of its path passed through farmlands and open areas. Only a few sturdy buildings were directly hit. Because of this, the damage seen on the ground only matched the EF3 level. At first, there was even a discussion about whether it should be classified as EF5 because of the extremely high wind speeds recorded by the radar. But later on, the official rating from the National Weather Service remained EF3 because that is what the current standards for using the EF scale dictate. Not everyone agreed with that decision. Many meteorologists and tornado researchers believe that nowadays, damage alone should not be the only basis. For them, if there is modern radar that can measure the true strength of the wind, that should also be included in classifying tornadoes. This issue is important because engineers use this kind of data in designing hospitals, schools, bridges, and other important infrastructure. If the true strength of tornadoes is incorrectly estimated, the durability of buildings built to withstand future disasters may also be insufficient. Even though the official rating of El Reno hasn't changed, there's one thing it definitely changed. It changed the way experts look at tornadoes. After this incident, storm chasers became more cautious when approaching large wedge tornadoes. There used to be parts of a storm that were considered safer to approach, but El Reno showed that the direction, size, and movement of a tornado can change within just a few minutes. The increasing number of storm chasers on the roads also became a topic of discussion. With every major tornado, hundreds or sometimes even thousands of people follow the storm to take videos. When they all converge in one place, they can block the roads needed for quick evacuation. On the day of El Reno, many residents also evacuated immediately because the memory of the devastating Moore tornado that struck just a few days earlier was still fresh in their minds. There was heavy traffic on some major highways. Fortunately, the El Reno tornado weakened and dissipated before it reached the worst of the traffic. According to experts, if the tornado had reached that area while the vehicles were packed together, There could have been even more victims. Despite all the tragedy, El Reno also made a significant contribution to the field of meteorology. It's now clearer as scientists understand that there are tornadoes that can rapidly widen in just a few minutes. They also learned how dangerous multiple vortex tornadoes are and how hard it is to track their internal subvortices. The data collected from mobile radar and from the instruments left behind by research teams are still being used today in the study of tornadoes and in improving weather forecasting. To this day, the El Reno tornado remains unique, not only because it is the widest tornado ever recorded in modern history, but also because it showed that there are still many things about nature that people do not yet fully understand. Despite the most modern radar, satellites, and computer models, there are still times when nature can surprise even the best experts. And perhaps that is the most important lesson left by the El Reno tornado. As we continue to study the weather and develop more advanced technology, we should never lose our respect for the power of nature, because in just a few minutes it can change everything.